Hey everyone, let's see what we gotta deal with today. Okay, so we're doing 5.44. Okay, computer architecture. Okay, in fact, I once took a course on computer architecture, right? So it's something I'm familiar with. Okay. Anyways, a short value is stored in a 16-bit. Okay, write a program that prompts the user to enter a short integer and displays the 16-bit for the integer. Okay, so here are sample runs. Given 5 is off, okay, 5 is dead, and minus 5 is dead. Okay, you need to use the bitwise as a hint. You need to use a bitwise right shift operator and the bitwise and operator, which are covered in appendix G. Bitwise operations. Okay, so here's the deal. The thing is, you see, I don't like using hints, right? But it doesn't mean you shouldn't. Okay, so here's what I'll do. I am not gonna bother myself using the hint that was given to us. It's like one of those exercises where they actually refer you to a program which is already written for you. I don't like bothering myself with those. Okay, so here's what I'll do. I'll write my own solution which has nothing to do with these bitwise operations. Okay, but I dare you to make sure you do so. Okay, make sure you use them. However, I'm not gonna use that approach. Okay, here's what you've got to know before I even continue. I genuinely believe that you've got a huge potential, and the reason why I'm here, the reason why I'm making all of these tutorials is so that I can give you guys out there push. Because I mean, honestly, I remember when I was actually taking a computer science degree, when I was actually new to programming, I mean, a lot of stuff was confusing for me. But then as the time go on, that's when I realized, you know what, as long as you give yourself time, you can accomplish incredible things. Okay, so enough now with the speech. Let's continue, because this is gonna be a long exercise. Okay, so here's what I already done. I created a scanner and I'm retrieving user input. Okay, so here's what I want to do first. I want to determine on which category does a number belong to. Okay, and that, in simple terms, what I'm saying is I want to check whether I can represent a number using a 4 bits, using 8 bits, using 8 bits, using 12 bits, or 16 bits. Okay. Okay. Here's what I'll do first. I'll have a variable to tell me whether a number has been categorized. Okay, at first I'll simply go false. False, okay. Determines whether a number has been categorized. That's not how you spell categorized. There's no R. Okay. Okay. What else do I want? I wanna have bit representation, and I will store it in a string bits. Okay, and I told you guys it's gonna be a pretty long tutorial. Okay, so now I wanna have, this is a starting index. I'll tell you in a moment what is it used for. This is a starting index on the 16-bit string or number. Okay, this string right there. Okay, so here's what I want to do now. I want to deal with numbers that can be represented by 4 bits. Okay, I'll simply have a for loop which will I'll go while I is less than or equals to 3. What I will then say oh, I forgot something. Remember, I told you guys I've gotta know on which category a number belongs to. I did not declare my category string. Okay, so here's what I'll do. I'll go category method. I'll explain in a sec what is this for. So it's 2 to the exponent of I, right? Yeah. Let me show you something, you guys. Or before I do that, let me just put a comment here. Deal with numbers that can be represented by 4 bits. Okay, I'm hoping you guys are familiar with number systems, because this is exactly what we're dealing with here. Okay, check this out, folks. I've gotta have a way to deal with all these zeros to the left of a given number, right? All these numbers to the left of a given number. I mean, for a positive number, I mean all these numbers, all these zeros to the left, the leftmost zeros, basically. That's what I'm trying to say. That's why I've got that over there. Okay, however, the way I'm dealing with my string, I'm starting from right to left. So you see this one over here, it's actually nothing else but 2, because these indexes, the index start from 0. So 1, that one over there, I mean that 0, the one that is highlighted, corresponds to index 1. Okay, and that one there, that 1 over there corresponds to index 0, 1, 2, right? So that simply says that the very first one there corresponds to index 0. Okay, so I'll start from here, from right to left. Okay, however, since strings are read from left to right, that is to say that first 0 corresponds to index 0, the second 0 corresponds to index 1. What we want to do is to flip our indexes. What do I mean by that? So, from strings point of view, okay, that 1 over there is actually index 15. So that is why I'll treat it as index 15, even though that it is actually index 1. I don't know if I'm creating confusion there. Okay, and if I am, perhaps we'll have clarity as I go on coding. Okay. Okay, what else? Okay, so now I wanna code if number in fact the absolute value of number, because I want its positive value. If number is greater than or equals to 0, and and the number is less than category, and the number is less than or equals to category. Oh, damn. How could I be so stupid? Let me just make that a short, because actually category is a number. Okay. I'll simply go bit equals to how many zeros we've gotta have, because we've gotta have 12 zeros here. So it's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. What we'll then say, we'll update our starting index. We'll make it 3, and then we'll say that categorized, we'll make that true. So essentially what we're saying is, so it's 0. Given that a number can be represented by 4 bits, which means these are the bits we are concerned about, the rightmost 4 bits. Okay, so in this example, these are the bits I'm concerned about. Okay, so that simply means that all the first 12 zeros, they'll stay as zeros, right? Given that our number is positive. Okay, so what I'll then say is that my my starting index is now what? My starting index is, because the rightmost one is index 0, then 0 is index 1, and then 1 is index 2, and the 0 next to that 1 is actually at index 3. So that's why we will start at index 3. That's why we have starting index there being 3. Okay. Ooh, again, I don't know if I'm creating any confusion, and if I am, I don't know what else I could possibly do other than trying to answer your questions. Okay, let's continue. We're basically gonna be dealing with 1, and our approach we'll keep doing one and the same thing. Now we wanna deal with numbers that can be represented by 8 bits. Again, what I'll simply do is to do that right there. However, this time around, I'm starting from index. I'm starting from index 4. And going all the way up to index 7. However, I'm only doing this because a number can only belong to one of the 6 groups. It's either belong to the first group, which contains numbers that can be represented in 4 bits, and the other group contains numbers that can be represented in 8 bits. So you cannot have a number that can be represented in more than in 2 or more ways, right? Okay, so that's why right here we've gotta execute this statement only if our number is not yet categorized. Okay, again, what do I mean by that? We gotta start from index let me scroll up. So this right here, when dealing with the 4 bits, we've got 2 to the exponent of 0, which is 2, plus 2 to the exponent of 1, which is, we've got 2 to the exponent of 0, which is 2, and 2 to the exponent of 1, which is, we've got 2 to the exponent of 0, which is 1, plus 2 to the exponent of 1, which is 2, that now we have a 3, plus 2 to the exponent of 2, which is 4, now we have a 7, plus 2 to the exponent of 3, which is 8. So we've got 15 right here because it's 7 plus 8. Okay, so now there we've dealt with all of those. So basically this is only for numbers less than or equals to 15, right? That should be it. Starting from 15, we're going downwards all the way up to 0. Okay, now what if we have our number is something greater than 16? So that's where we'll start from. 2 to the exponent of 4 and then go 2 to the exponent of 4 plus 2 to the exponent of 5 plus 2 to the exponent of 6 plus 2 to the exponent of 7. Okay, once we're done doing that, we'll have something more or less like what we had up there. I'm copying and pasting for the sake of minimizing time, you guys. Otherwise, this might take close to an hour or probably more than that. But again, I'll keep trying to make things as simple as possible. However, here's what we've got to change now in our if statement. Number 1, we've got to make sure that number is less than or equals to what? Oops. We've got to make sure that number is less than or equals to category. Okay, and number 2, we've got to make sure that number isn't yet categorized. Now we've got to minimize our number of zeros by 4. 1, 2, 3, 4 by 4 zeros. Okay, so that is to say now we've got 8 zeros to the left. So the first 8 zeros, it's like the leftmost byte of our 16 bits. It's like it won't be touched, it won't be altered, it will only contain zeros. We'll only deal with the rightmost byte. Okay, so and our starting index will now be 7. Right? Check this out. Remember, before our starting index was 3 because we had 0, 1, 2, 3, right? So the last 4 bits from left to right, so the last 4 bits were actually responsible for representing a number less than 15. Okay, now the last 8, it's no longer 4 now the last 8 bits are the bits that will be responsible for representing a number greater than 16, and I'm not quite sure what's the maximum boundary for that number. So now let's see on what index does it start on. So it's gonna be 0, 1, 2, 3, 4, 5, 6, 7. So that's why we've got starting index being 7 here. And then again, we're saying that the number is categorized. Let me copy and paste this again for the sake of avoiding too much time. We only have got to do a few things, and that includes changing that from 4 to 8, and then so it's gonna be 8, 9, 10, 8, 9, 10, and 11. Okay, and then the bottom part will pretty much look exactly like what we had before, except that now we're removing 4 zeros. Okay, now we're removing 4 zeros, so it's like now the first 4 zeros from left to right will be kept as they are. So the way the bits that will be used in order to represent our number are the ones starting from index 0, 1, 2, 3, 4 onwards. Okay, I don't know if I'm creating confusion there again. So our starting index now will be 11 if you're reading our indexes from left to right, because that's how we read our indexes. So it's gonna be 0, wait, it's gonna be 0, 1, index 0, index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's our index 11. We're reading again, remember we're reading from right to left this time around. In fact, starting index is actually assigned a value by reading your string from or bits from right to left as opposed to left to right. Okay, that should be it now, folks. Now it is time, we're almost to the end of this tutorial, so that's why I will simply say now, we've gotta find a way to determine which, let me put this down, determine which bits are zeros and which bits are ones. And you will simply do that by having a variable called sum. We'll use this variable called sum in order to determine. Okay, so I'll simply go int I, starting from starting index. Depending on the value of our starting index, if our starting index is 4, for instance, that is to say we're dealing with a number that can be represented by 4 bits. Okay, so our starting index there, it will be 0, 1, 2, 3. It will be 3. So that loop will basically start from index 0, 1, 2, 3 when reading from right to left, and there will be index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 if you're reading from left to right. Okay, so basically the loop will forget about all the numbers to the left of our starting index. Okay, in this case I start from there and I'll go while I is greater than or equals to 0. I'll simply decrement my I. If my sum plus that is less than or equals to number, but I'm in the absolute value of my number. Again, I understand most of you guys out there would make an argument that this is more complex compared to using the hint that was given to us, and you're absolutely right. as I just mentioned, I don't like using hints, especially when teaching you guys. I use them on my own things, but when teaching you guys, I feel like I always think it's better to do everything from scratch. That way you guys will see how to go about thinking about a problem. Anyways, let's continue. Here's what I'm doing. Suppose we were given a number like 13. So here's the logic. 9, not 13, 9. Okay, so I'll start from that index, and that is index 0, 1, 2, 3 when reading from right to left. So I'll check 2 to the exponent of 3, right? That will give me an 8, right? Okay, then I'll add that 8 to my sum. So now my sum is 8. Now we'll check 2 to the exponent of 2. Okay, remember our number value is 9. So I will check now 2 to the exponent of 2. I will try to add 2 to the exponent of 2 to my current value for sum, which is 8. And we know that 2 to the exponent of 2 is 4. So it's going to be 8 plus 4, which is 12, which actually exceeds our number. So we're going to have to ignore the second index, which is index 2, right? Now we go to the index 1 less than that, which is index 1. So I'll now go 8 plus 2 to the exponent of 1. So that's going to be 10. But 10 is greater than our number, the number that we will give our program, and that number was 9. We all know that. So we basically ignore that index again. So we go to the last index, which is index 0. So it's gonna be 8 plus 2 to the exponent of 0, which gives us 9, which is exactly what we need. So what we're gonna do is we're gonna know right there and then that we have a 1 on that index. So we got 2 ones, by the way, a 1 on index 3 and a 1 on index 0. Okay, so those 2 ones correspond to 9. So that is the logic behind this loop over here. I would understand if you guys have had enough already with this exercise. Okay, so as I just said, if 2 to the exponent of I plus sum is less than the number that was given to the program, I add that I add 2 to the exponent of I to my sum, and then I simply go bits. I put a 1 on my bits. Otherwise, I know I would have to put a 0. Don't get excited. We're not done yet. In fact, there is quite a lot that needs to be done. Okay, remember you guys, I asked you before. In fact, I'm hoping you guys are familiar with number systems. Okay, because there is a possibility that a number that was given is actually less than 0, and that is to say a number is negative, just like in the second case here we were given -5. So here's what we want to do. I'll use a 2's complement approach, and I don't have time to explain what the heck is that. If you don't know what the heck is that, what you gotta do is to jump onto appendix. I'm not quite sure whether it's G or what, but back in the textbook, or you can Google it. Just look at the how does 2's complement work on under number systems. Okay, and then you're good. Okay, so here's what I'll do. I want to check if my number is less than 0. Oops. You can pause this video, take a deep breath, and then come back to it. That is totally acceptable, okay? Okay, so we've got to have a negation. Okay. Oh, in fact, you know what? I'll just go negated bits. Okay. Because that's how 2's complement work. You first negate all bits and then you add 1 to them in order to obtain your negative number. Okay. So what we gotta do, we've gotta create negated bits. We will simply do that by a loop. Int I equals to 0 is I less than bits dot length I plus plus. Okay, now negated bits here's what I'll do. I'll check if bits that I'll check this if it is equals to 0. If this is the case, then I know I need to add 1. Otherwise, I need to add 0. I mean, that should be pretty much it. Okay. Oh, by the way, I'll only give out one solution on this exercise since it's a pretty long one. Now what we want to do is to represent a 2's complement of a number. Okay, so here's what I'll do. Okay, it is complement number in a reversed order. You'll see in a moment why we're having it in a reversed order. Reversed 2's complement. Whew. Oh, before I do this, what I've got to do is to have another variable which will tell me is 1 inserted. At first I'll go false. Perhaps it's better I put a complement here. Determines whether or not a 1 is inserted to a negate to the negated bits. Okay. Okay, now bits index. Right here I'll start from the last index of my negated bits. So negated bits dot length -1 while bits index greater than or equals to 0. Bit index minus. Okay, I'll check now. If the current bit is minus, in fact that is exactly what I want to do. If that is the case, it's bit index instead of I. So if I've got 0 and 1 is not yet inserted, and 1 is not inserted, again I cannot go into the details. How does the two's complements algorithm work? Cannot go to the details defining that. Okay, so you're gonna have to do that yourself. Okay, if this is the case, then I have to add 1 on my reversed 2's complement. Reversed 2's complement. Reversed 2's, not 2, it's 2's. Oops. Not now. I really hate it when this machine becomes slow. Okay, if that is the case, if we see 0 on our it's not on our bits, on our negated, because you've got your bits, you then negate them, and then finally you add a 1. That's how your 2's complement algorithm work. Negated bits. Okay, if you see a 0, we simply add 1 on our reversed complement, and then we finally say that is 1 inserted. We say that's true. Yes, we have inserted a 1. Else if there's another case, if we see a 1 and we haven't yet inserted a 1, in case we see a 1 on our negated bits, let me try to make sure that everything is visible. Okay, now in case we see a 1 on our negated bits, remember our negated bits, we're reading it from right to left. Okay, in case we see a 1 and we haven't yet inserted a 1, which is the second step of the 2's complement algorithm, what is it we'll do? We'll simply insert a 0 on our reversed what? 2's complement. Okay, otherwise, if none of the 2 above conditions are met, what we'll simply do is what we'll simply do is to add the exact bit that we read from our negated bit. Okay, so we'll simply add the exact thing we read from the negated bit. At bit index. Bits dot character. Oh gosh. Whew. I don't know if it's because it's freaking sunny today. Oh, I kind of having hard time now. Okay. What else? Oh, that is pretty much it. That is pretty much it. Once we're done with our loop, the next thing for us to do is to create a tools complement bit. Tools complement bit. This is the final step. No wonder they gave us a hint, because if we had to use bitwise operations, the right shift and the end operator, I bet things would have been way too simple. We would have been done a while ago. Okay, int bit index is equals to, we'll start from reversed tools complement last index. We'll start from the last index of our reversed tools complement. Okay, while bit index is greater than or equals to 0, bit index minus. Now we're creating our tools complement. Tools I know you might say we've used a ton of variables here, but I did it on purpose. I wanted everything to be as crystal clear as possible. Reversed tools complement, because the problem on its own can be confusing, so I didn't want to add more confusion by using few variables. The confusion that is created by exercise itself is enough. Okay. What do I want to do? I want to use char add bit index. I'm hoping people are clear here. In fact, we could have simply used a string builder here in order to reverse our reversed tools complement into the exact thing we want, right? That would have been better. Okay, but you guys don't know yet about string builder, which is absolutely okay, because we're not there yet. Bits. Okay, so those are our bits. Now finally, in fact, this portion is only taken care of negative numbers. Finally, what we'll simply do is to go system. I've got to grab a snack after this. I feel it. I really need something to eat. Okay, decimal value. In case I made a mistake, I'll literally faint with this sun burning. I cannot stand mistakes. Has is a 16-bit value to complement. Oops. Now I can't even spell 2's complement. Oh, in fact, what I need right here is bits. Okay. Let's hope shit is gonna work well. This thing is gonna work the way we want it to. And if it doesn't, I don't even want to say what's gonna happen. Let's try 5. We're not getting shit. And I will tell you in a moment why. Oh, in fact, we got something. We got exactly what we wanted. Let's try -5 this time around. Maybe it was still computing. No wonder we had that. Boom! We've got exactly what we want. Let's try 15. Oops, it seems like it works, but I don't know if you identified a typo somewhere or a logical error or whatever that you found suspicious. Please let me know. What I'll simply do for now is to say I'm gone.